talking about signal processing, of course, most importantly in audio. He's an auditory perception specialist. He's an expert in audio processing, speech processing. He likes mathematics, programming, everything that you all guys need to know and to excel in order to have a better understanding of what it means to do audio signal processing. Ultimately, Professor Tarr gave me permission to share his contact information so you can reach him at with any given time, of course. So you can find his email as well as his LinkedIn profile there. And in addition, one of the most important things is that I've been doing more events throughout NYU, not only in signal processing, but in all other aspects such as AI, machine learning, for example. But most importantly, right now, Professor Tarr is he wrote the book in audio signal processing. The book's name is Hawk Audio. It was sponsored by the Audio Engineering Society. And well, he's going to be talking about that, some techniques in real-time processing. And as he mentioned before, if you have any questions that are relevant to what he's doing at that moment, feel free to raise your hand or send a chat. If not, we are going to have a small Q&A session at the end of the coding demo. And before we start, don't forget to join our LinkedIn groups or Instagram. I also created a Discord. So if you guys are interested in learning more about MATLAB, Simulink, about the events that are going on at NYU, please do that. And for anyone that's working or has classes at this moment in time, I'm going to be sharing the recording of the webinar itself, as well as any scripts involved. And you can find that next week at the MATLAB at NYU official website. So please feel free to join that as well and take a look. And having said that, Professor, thank you so much for your time. I'll give the stand to you. And yes, take it away.
Yeah, I appreciate the introduction, Chris. It's a pleasure to be here today with all of you. I'm coming to you from Nashville, Tennessee. I know that many of you are going to be coming to the webinar from NYU or a few other places, and I'm grateful that you would spend the afternoon just learning about and talking about some things related to computer programming and signal processing, specifically for audio. I expect that that's at least the bare minimum interest of everyone attending the seminar. And you may have various degrees of background and experience related to signal processing or programming or audio, some mixture of all of these, or some, experience more than others. And I hope that there's something for everyone involved. My plan is to primarily do live coding today as part of the seminar so that you get an opportunity to see lots of things in action in terms of working with signals and creating audio effects inside of MATLAB, and then maybe cover some things also related to synthesis, and also teach a little bit about some of the theory for understanding what we're doing to signals and changing them in some way. I would describe a lot of my work that I've done related to computing and audio related to audio effects. So things that process the signal in some way. That's obviously one area out of many that you could get involved in related to computing and audio. But that's, I guess, what I will focus on in my seminar is that aspect of audio. So I spent a lot of time working with MATLAB as a student. That was what I learned when I was studying electrical engineering. And I then incorporated it into a lot of my teaching. I'm at Belmont University, and I teach classes, a lot of them that overlap between computing and signal processing. So MATLAB is a great tool and resource for being able to do those things. And then I also do a fair amount of software development on commercial products and audio plugins that are released. And so MATLAB is something that I use a lot on a day-to-day basis for prototyping in proof of concept for a lot of the effects and things that I create. So with that, I guess I'll just jump into my plan for the talk today. I'm going to switch over. Let me get out a full screen from my PowerPoint and switch over to MATLAB. So my plan was to just work off of this script and be able to go through and demonstrate a handful of different audio effects, from things that are relatively simple up to things that are more complex in terms of how the data inside of a signal is processed. I hope at least many of you are familiar with the basic syntax of MATLAB in terms of working with variables, and then also variables and calling functions and scripts. And also a big thing is going to be working with arrays. So I will cover a little bit of those things, whether you are familiar with how audio works and is represented inside of MATLAB. I want to make sure we're all off on the same foot for things. So I just have this M file that I'm working off of where I have imported an audio file that exists on my computer's hard drive. And then the plan is just to do different things with it. So these are some functions you may or may not have come across before when you're dealing with audio things. So one of the things is to read in that file. You give it a string, and that returns two things from it. It can return the actual signal itself to use, and then a sample rate related to it. And then I have this function down here for playing back the sound. That's how you can listen to it. And then I'll also do some other things here in a second, including plotting it and that kind of stuff. So I'll play this back so you can just hear where we're starting from. The idea is to get the file off the hard drive and then listen to it back. And it's a short 5 to 7 second long clip of an acoustic guitar. All right, so probably worth talking a little bit more about what we are working with in terms of our information. I'm going to do some notes along the way just to cover some things to make sure it's all clear. So when we have an audio signal, let's say it's captured by a microphone, we're working with continuous time here. It gets sampled and it's represented in our computer as these data points. And these are the things that end up getting put into an array in MATLAB. So here are basic measurements, and generally speaking, this is going to be within a normalized range from -1 to 1. So in MATLAB, what happens is we end up with this vertical column vector of values that are put in sequentially based on the data over here. So this might be a value of 0.4, and that's going to go as the first element in our array right here, 0.4. And we have the second element over here, maybe this is 0.6, and that's going to go in as a second element in our array. And then we have the third element, maybe down here is minus 0.8 as another one. And this is how our audio information is represented in MATLAB. So if you're new to this, a big thing to understand is audio is just a bunch of numbers, and those numbers are grouped together into something called an array. Other names for this will be a matrix or also a vector. And those are arranged based on the number of rows and the number of columns. If we're working with a mono audio signal, it has one column and a bunch of rows for the different samples in our signal. If we're working with a stereo signal, it has two columns and then many rows like this. So when I import the audio signal here in MATLAB and store it over here, we have these variables that get created, and I can visualize what's in this. Also over here, if you're familiar with MATLAB, you have something called the workspace, where you can see the variables that are stored currently in memory. So you have our signal here is 312,346 samples long. So these are the number of rows that are in one column. So this is a mono audio signal. It has a sampling rate. So the number of samples per second here are 4,100. So these samples, I can look at them. It's a lot of them to have to view. If I just come down here to the command window and print them all out, this is a lot of samples, right? I can't really make sense of this just scrolling through these numbers. I can also see sampling rate here of 44,100. So one thing we can do is listen back to it and hear it. Another thing that we can do is plot it. So I can come in here, say plot X. I'm going to comment out this one. So that's in MATLAB, the syntax for a comment is a line of code that's going to be ignored. is anything after a percent sign for it. So now if I run this, we can see something called the waveform, right? Hopefully you're familiar with this way of visualizing the signal. It is a plot of the signal's amplitude over time, some unit of time. In this case, we have units in terms of the sample number. So it shows sample number 1 down here and sample number 312,346 all the way over here. And that's what we're visualizing. So that's just some essential things for getting started. There is also another function that I'll mention that's worth knowing about called audio write. And with this one, what you can do is take some array of samples. I guess I should get this order of them correct. Maybe you put the file name first. Let me check for help on this. Audio write. To look at the documentation for it. So we put in a file name, that's a string, then we put in the array, and we put in our sample rate. And this is a way that we can store a new file. You would want to put in like a extension for it to be based off of a file type of an audio signal. And we put in the array, and we put in its sample rate, and now we can create a new file on our hard drive based on the data that we have in this array. Now, from this point forward in the webinar or the seminar, what I'm going to do is talk through how we can change the data in our signal to do something else with it. So we can end up with a different one, something that's been processed by some type of effect. So presumably then we could save it out on our hard drive and have a new version of it. So that's another valuable one to be aware of. So let me take you through some of the different audio effects of what we're going to accomplish. So the basic idea is we want to have some input signal X that goes into some system, some audio effect, and we get a new one out of that, like this. And this effect can be very generic or very simple. The first one I'm going to start out and talk about is how to change a signal's amplitude. Very common thing to want to be able to do. If you're familiar with audio that is being processed inside of a digital audio workstation like Pro Tools or Logic or GarageBand, these are going to be your channel faders, where you're changing the amplitude of the signal to raise it and lower it and do those kinds of things. So this operation is fundamentally about multiplying the signal, the samples in your signal. It's a very specific kind of processing where we're going to go through sample by sample in our signal and multiply it by a new value. So just to give you some ideas on this, if you have these individual values and we multiply them by different numbers, we can go through the thought exercise about, well, what happens if we multiply these things by different things? So if we were to go through and take this individual sample, and we're going to try to create a new array from it. So maybe I have one over here that I'll call Y. It's another array. And the idea is to take a sample, like the first sample from this one, and we're going to put it into the first sample of our output signal. That's what this kind of effect processing is meant to do. Take this sample and create a new one from it by multiplying it by something. So if I were to multiply this sample by 1, we would get the same exact sample back, right? And so you get in the output the same thing, 0.4, 0.6, minus 0.8. So that would be a way of multiplying the signal by something where you don't change it at all. This in audio is called unity gain, where you're not modifying it in any way. If we multiply this number by something that's greater than 1, so an example could be 2, right? We're going to double the amplitude of each of the samples in here. So 0.4 will become 0.8. 0.6 would become 1.2. Minus 0.8 would be minus 1.6. So this is a way of increasing the amplitude of our signal by multiplying it by a number that's greater than 1. We can also multiply these samples by things that are less than 1. So if we multiply it by 0.5, that's going to be a way of taking these numbers and making them less. So it'd be 0.2, 0.3, minus 0.4, right? That's decreasing the amplitude there. A few other ones worth mentioning. We could multiply our signal by 0. And if you multiply any number by 0, the result is going to be an array of all zeros. So that's a way that we could create silence. That's also a way of attenuating the amplitude of the signal on the decibel scale, which we'll talk about down to minus infinity on the decibel scale. One last one that I'll mention is if you multiply a signal by -1, what that does is it takes all the positive values and turns them into negative versions of themselves. So 0.4 becomes negative 0.4. Negative 0.6 becomes, or positive 0.6 becomes negative 0.06, and vice versa. That's a very specific operation that we use in audio that's called the polarity inversion. And in a audio software or on a mixing console, you see a button like this that's usually pressed if you want to do polarity inversion. So this is an operation that is accomplished in computer code by multiplying by -1 to just take the signal and flip it upside down. Makes things that are positive into negative and vice versa. So I want to demonstrate how this is actually coded because what we want to do is access the individual elements of our signal and go through them and create a new one for our output Y here. So I'm going to go back to MATLAB and I'm going to use a control structure in MATLAB called a loop, where we can do the same task over and over and over again. So if you're familiar with programming, you are familiar with the fact that lots of programming languages have this idea of a loop, where you have a section of code that you repeat over and over and over again. So here, what we want to do is figure out how many samples are in our signal so we can set that up as part of our loop. So MATLAB has some built-in functions for this. I'm going to use a variable here called n, capital N, to represent the total number of samples in my signal. I can check that and figure out that the length of my signal is total number of samples. Then what I'm going to do is go through a loop where I start at the first sample, sample number 1, and I go all the way up to the end of my signal, which is sample number n, down here. And I'm going to process those in the same way. So I'll start here. I'm going to create a counting variable and it's part of my loop. So it'll be for lowercase n equals 1 up to capital N. This means loop through these lines of code in between the beginning and end this many number of times, and then use a variable inside that I can use for the sake of indexing my array. So in MATLAB, if we have an array X, and we want to access an individual element from it, I can demonstrate this quickly down below. Let's say I have an array here that is 4, 5, and 6. Oops. So this is going to be a column vector. If I want to access one of those values, I could do A 3, 1, and that gets out the third row in the first column of this array. So this is the method that I'm going to use to go through all the samples of my signal in an iterative way inside of the loop. So I'm going to start here using that variable lowercase n that goes from 1 up to whatever the length of my signal is. Now I can access that, and I'm going to assign it to a new variable here I'm going to call Y, add a current time sample like this. Okay. So right now it just takes the first sample of X and it assigns it to the first sample of Y. It takes the second sample of X and assigns it to the second sample of Y like this. Okay. There's a thing that is a good practice to do in MATLAB when you're working with arrays like this is to, it's giving me this warning to say, hey, this is changing size. You're increasing the size of Y every time. If you can pre-allocate it, that's great. So I'm going to do this step. It's a take a little while to explain, so just bear with me on this. That what we're going to want to do is initialize Y to be the same size as our signal X. What this does is it creates an array of all zeros that's the same size, so that we're not having to change the size of Y every single time we go through the loop. We're just overriding a value of 0 in here. So if I did zeros of 5, 1, that creates an array for us to use that's the correct size. So that's just a MATLAB step for making things run faster. Okay, so the idea is here we're going to have some gain that we want to apply to our signal, right? We said if I multiply by 1, you get the exact same signal back on it. If I multiply here by a value that is greater than 1, so I can multiply by 2, then we'll get a signal that's larger back. And I can visualize those things down here. I will create, let's create an array here, T, that we can use to plot our time vector in seconds. So we're going to create a new variable here called t, and we're going to need to know t is going to be an array. This is some MATLAB syntax for this to go from time of 0 up through time of n-1 multiplied here, the whole array by ts. So I know this is kind of getting into some complicated MATLAB syntax if you're new to it, and I wish I had more time to just focus on this, but I want to cover more things. So ts is going to be the sample period, which is 1 over the sampling rate. What this allows me to do now is when I do this plot, I can plot and label the x-axis time in terms of seconds, like this. And I'll also be able then to plot with it y compared to x. So I can plot in here t and y on the same plot. There'll be 2 drawings. There'll be the original one is going to be in blue, and the second one, our processed one, is going to be in red for y. So here's the result of multiplying by 2 on our signal. So believe it or not, there are 2 signals. The red one is getting drawn right on top of the blue, and I can zoom in and see the blue one, the original one that is underneath it. So this is our result of when we multiply the blue one. Try to enlarge this a little bit. Multiply the blue one by 2. We increase the amplitude on it, and it gets visually stretched out vertically for us, and it then occupies samples that are above the ones before. I'm going to add some MATLAB code here to clear things out whenever I run this script multiple times. This just clears out my workspace fresh each time and clears off the command window and closes all the plots. So this time I'm going to change this to have a value of less than 1. So this is 0.5. Run the script again. We get a different plot, and this time we have dropped the level of the signal. So this one will be lower in amplitude compared to the original. If I multiply here by 0, that would be where you end up with a red line of silence. So we've decreased the amplitude all the way down to 0 on this. The other one that I mentioned is to multiply by -1. So have a gain of -1, apply that to our signal. What happens is you take all the samples and you invert them. So if I zoom in right here, what you see is everything that was positive now becomes negative and vice versa. So that's the polarity inversion. Just some good things to know in terms of basic operations of applying a multiplication to our signal. One quick thing I'll mention while we're in the process of doing these basic operations of a single value with our signal is you can also add values to a signal. So this is called a DC offset, and I'll show you what it ends up looking like if I maybe do a DC offset here of 0.5 and add that to our signal. This name for it comes from the days of electronics when you would have digital, or not digital, direct current that's applied to our signal. And so the stretching of the amplitude is not the way that we would visualize it. Instead, it's shifting the waveform up here by that amount of 0.5. And then all the numbers are centered around there as our DC offset for it. This is typically not something that we want to listen to or play back over our speakers. It won't damage your speakers, but you're not having the speakers operate in its traditional region. And so we only really use this DC offset as part of like certain kinds of effects and stuff that we'll come back to later on with time allowing. All right, so what's maybe more interesting is to go back to this idea of gain that we're going to apply to our signal. And if you have any experience with audio engineering and using a channel fader or things like that in a console or digital audio workstation, you are typically working with a different range of values, a different scale called the decibel scale. And you have values like 0 dB for unity gain, which means no change in the amplitude, or you have a value greater than 0 for like +6 would be what audio engineers think of as a rule of thumb of doubling the amplitude, or -6 is cutting the signal in half. So what we need is a formula to be able to convert a value that you might get from a channel fader or a slider and convert it to a linear amplitude to be able to use. So if we had a dB gain here of +6, what we need to be able to do is convert that to linear. And there's this logarithmic relationship between decibels and linear amplitude. In this case, I guess it might be worth writing out because it's a common thing that people come across when they're first getting used to signal processing is dealing with the decibel scale.
Eric, quick question. There was a question in the chat.
Sure.
It is about, is DC offset typically considered noise? I have seen situations where I've had to remove the DC offset from a real-time signal code. I think that's the comment.
That's a great question. I guess it depends on where it's originating from. Sometimes it is added to a signal due to interference. And the interference signal that gets combined with the audio is something that we would consider to be noise. So in that case, I would absolutely consider it to be noise or interference that is impacting our signal that we would want to remove. There are other cases where we are intentionally adding it for the sake of, like an example I'm going to demonstrate here in a little bit, is for amplitude modulation or the tremolo effect. And in that case, I wouldn't describe the DC offset if it's getting added unintentionally, then yeah, I would consider it to be noise. In other cases, we just have to know that we're using it appropriately and in the right situation. So I think that's a great question.
Thank you. That makes sense. Thank you.
So back to the decibel scale on this. So there's this conversion that happens between linear and decibels. And if we have some amplitude on the decibel scale that we're trying to calculate, this is done by using this formula that goes back to Alexander Graham Bell of 20 times log base 10 of your linear amplitude. These are subscripts that I'm giving to these things, divided by some reference. So usually this reference for us is just going to be 1, which is going to be that normalized scale that we're working off of. But there are some situations where we might have a different reference. So just be aware that sometimes that's necessary. But for now, let's just say that this is equal to 1. In our case, what we need to do is rearrange this, because typically if we have a channel fader, something on a console that audio engineer is moving around, what we know is the decibel scale, and we need to convert over to linear. So we'll have to rearrange this and do it where we are going to take this and divide by 20. So we have amplitude dB divided by 20 equals log 10 of amplitude on our linear scale. This is what we're trying to figure out. This is our unknown over here. This is known. And then with logarithms, the way that works is it's move it over to the other side, it's equivalent to 10 raised to the power of this thing. So 10 raised to the power of amplitude dB divided by 20 is equal to our amplitude on a linear. Oops. This is what I've called gain in our code that we're then going to multiply by our signal. So if you're an audio engineer, you're doing some software, you know you're trying to accomplish this on trying to change it in some way on the decibel scale, then this is the formula you would want to use. 10 raised to the power of our dB gain divided by 20. And this is what we would apply to our signal. So this is the case when we're going to double the amplitude like this. And we could also do this by -12. So that's a quarter of the amplitude on it to bring it down from there. And, you know, then this could be really any value. It could be -16 point whatever we want, and able to apply the appropriate gain to our signal this way. So that's plenty about just changing our signal's amplitude, but I'll say that it is such a common kind of operation you want to know how to be able to do with our signal, then that is a good one to feel confident in knowing the typical ways that this is accomplished. So next I want to do is talk about how we can synthesize signals that might be useful for stuff. So right now what I've done is I've imported an audio signal right here. And what I want to do is instead look at some ways in MATLAB of synthesizing basic kinds of test signals like a sine wave or square wave. These are oscillators that are used for a lot of testing, but they're also used as kind of the basis for a lot of other kinds of synthesizers. So you might want to have a good idea about how to use these. So instead of importing a file, what I'm going to do is create my own one. I'll call this X over here, like this. And now what we're going to do is specify the things that we want to be included in it. So instead of importing a sample rate, I'm going to make my own sample rate for this sound file that I'm going to create. So FS is going to be 4100. Hit Siri by accident. Sorry. Should be back now. Okay. 44,100. And now I'm going to create a time vector to be able to use over here. So I'm going to move this one up, both of these things up, because I'm going to calculate my sine wave based off of time in seconds. I need to know the length that I want for my signal. So this one I can specify based on a length in seconds. Here, let's make it 3 seconds long. Okay, so now this is the total samples are going to be a length in seconds times the sample rate. It's a good idea if you're working in MATLAB and this is going to be the number of samples in your array to make sure this is an integer. When you're working with indexing arrays, you can't index a fraction of an array, an element in the array. So I'm going to make sure this is going to be an integer. That way I could do, a length of seconds to be some number that I wanted like this and ensure that I'm always going to end up with rounding it to an integer number of samples. All right, so this is a good place to start. I have a time vector t. I'm going to remove these things. I don't need them right now. Say that X is going to be this new array. And for this, now I'm going to use some built-in functions to MATLAB for being able to calculate these different kinds of test signals. So the formula we can use for this comes from the equation for a wave. That we'll use is that our signal X is to a sine of 2 times pi times the frequency times t. So this is our time that we're going to have in seconds. We can specify a frequency here. And if we wanted to, we could even apply that linear amplitude out front and call that A. So this is what we would have. We can specify this frequency in hertz for our signal. So let's set that. We'll say F is equal to, how about 220? So this is 220 hertz. New sine, 2 times pi, so that's built into MATLAB. F times, now we have this whole array T that we want to be able to use. And so I just need one of the samples of T that we're indexing out of the whole array. F here is going to be an individual number and T is going to be an array. So we just need that particular time that we're going to use for this. And this eventually just calculates a sine of some phase angle that's based off of our time vector. All right, so this would be a good one to listen to so far. Let me go ahead and do this. So you should be able to hear, we'll see if I have any bugs, but I think you should be able to hear my sine wave. Be careful with the audio volume on your computer. Oops, I realized that this is not a column vector. So one of the things I messed up here is my syntax for this is it created a horizontal row vector. That's one that has this dimension to it. but I'm indexing based on a column vector. So I need to transpose this to turn it into the right dimensions over here. So there's my 3-second long sine wave. I'm going to not listen to this, but I can plot it, and you can see what happens if I have like a lower frequency. This is not one to listen to, but here's one that I'll have it repeat 3 times over the course of a second. So here's my sine wave that I've generated that goes through these cycles like this, and I can change that to 10 cycles for every 1 second, like this. And that's your basics of synthesizing a sine wave. The nice thing about MATLAB is you have some other built-in functions for creating other kinds of test signals. So we could swap this out and create a sawtooth wave. It looks like this. So instead of having those curved rounded shapes of the sine wave, now we have this ramp that goes up that gives us the shape of the sawtooth. And this one we could also listen to if I switch this back. To maybe 220. Let's make this 100. So it has a very different kinds of tone or timbre to the signal than a sine wave. It's because a sawtooth spectrally is comprised of many different frequencies. I'll use this opportunity to show some code that I have included in the textbook that I have written, the Hack Audio textbook, as code to be able to use. This is publicly available. It's not something that is built necessarily into MATLAB, but one's code that you are more than willing to use if you ever need it for certain kinds of things. So I have all the code up for the book on this website. Let me see if I can find it. Here you go. Sorry, I have the WebEx banner in my way. So this is the GitHub page for the textbook. It's GitHub Hack Audio textbook code here. And whether or not you have the textbook or not, you can access all these chapters of code. If you do have the textbook, you can, all the textbook code is included in the print version of it, as well as here that you can download and be able to run yourself in MATLAB. So the function that I'm going to use is in this one is called plot, time, and frequency. So it's just a small modification to the plot function so that you can see both the waveform and the frequency spectrum of the signal. So this one can be downloaded and put in your MATLAB directory to be able to use. This is part of a chapter that's all about different types of synthesis, which I'm now going to be able to demonstrate. So I have that file in my MATLAB working directory right here. And now if I were to go in and plot X, plot TF, the time and frequency of X with the sample rate, we see the result up here in the top is our waveform. And I can zoom in on our sawtooth wave and see that up here. And then down here, we can look at the harmonics that are part of the signal. So here we see that this is a sawtooth that has harmonics at 100, 200, 300, and 400. So even and odd harmonics all the way up the spectrum towards our Nyquist frequency. So that's another way to visualize the information and understand and appreciate what's part of one signal compared to another one. If I go back to my sine wave, this has a very different spectrum. It just has a single frequency, a single harmonic that happens at 100. We can also compare that to a square wave, which is another built-in function to MATLAB. And this one, if we look at the waveform, it's kind of self-explanatory. What you see for a square wave is sections that are the maximum amplitude and then the minimum -1 going back and forth. And square wave is known to be comprised of primarily odd harmonics. So here we see 100 hertz, 300 hertz, 500 hertz, 700 hertz, all the way up the spectrum. Just so happens that the way that this square wave is synthesized, we also end up with a bunch of aliasing. If you're familiar with aliasing in terms of a concept for sampled information, what happens is we have all these frequencies that get folded over from our Nyquist. And you see the aliased frequencies actually coming down here. And that's the ones that are lower in amplitude, are because of a lot of aliasing from the way that we synthesize this signal. So that's just some more stuff about synthesizing signals. What I'd like to demonstrate next is how we can put these ideas together to be able to synthesize signals and apply them in interesting ways to our, like an audio signal like we had here. So the next effect that I'm going to demonstrate is one called amplitude modulation. Let me explain this one and describe then some background on it to appreciate what we're going to put in our code. So amplitude modulation is used for a wide range of things when it comes to audio signals. So the one that we'll primarily focus on is for tremolo. So tremolo. This is where we have like a amplitude pulsing that we're going to apply to our signal, where it increases in amplitude and then decreases in amplitude. And it does so in a repeated fashion relatively quickly, several times a second. And that's done so based off of typically like a special signal we'll call a low frequency oscillator. Low frequency oscillator. So that's a good term to be aware of, the LFO. That's the one we'll focus on. Amplitude modulation is also used for other types of things. So there's another category of effects that we would consider to be, at least from a perceptual standpoint, distinct from tremolo. That's one is called ring modulation. That is accomplished using a very similar basic operation of having like a modulator that you apply to some other kind of signal. But usually these are things that are within the audible frequency range, whereas a low frequency oscillator is typically under or below the range of human hearing, in the range of like 1 hertz or 2 hertz that we're going to use for this LFO. I'll also say that amplitude modulation, at least this method, can be used with a high frequency signal above the range that we would hear, and that was the basis for radio. So AM radio is based off of this same operation that I'm going to show you for tremolo. Instead of using a low frequency, it uses a higher frequency, and that's when you get into the range of kilohertz kinds of things. But let's focus on this effect, tremolo, and just know that the same operation can be used to accomplish other things as well. So here we're going to have our input signal, X, and it has different sample numbers. Okay, so it varies. This is a function, an array that varies over the sample number. You get a different value for 1 as you have sample 10. Up to this point, what we accomplished was this multiplication by some scalar value. So we called it gain on this, but it could be just any variable. I'm going to call this one M. Okay, and that value was fixed. It was the same thing for every sample that we applied to our signal. What we could do is have this multiplier also vary over time or vary over sample number. So now I'm going to make this a function. It's going to be an array, just like this is an array, and we'll multiply the corresponding samples between these, and that will allow us to get our output Y of N. So this is going to be called our modulator. In terms of amplitude modulation and tremolo, this input is also sometimes called the carrier for it, and then this is our output. So visually, in terms of arrays, the way this worked is we had an X, and it had the samples 1, 2, 3, 4, 5, 6, 7. These are sample number 1, 2, 3, 4, 5, 6, and they'd have values like 0.4, 0.6, 0.8, on and on and on. We create our output over here. And our first operation of signal gain was to take this sample and multiply it by a number like 2. We multiply this one by 2, and that would give us this one. and we take this one and we multiply by the same number and it gives us this one. And we take this one and we get it like that. So we multiplied here by the same thing. This is our multiplication operation. Multiply by the same thing for every sample to get an output. And this time, what we're going to do is we're going to say, well, what if we make this something that varies over sample number? So this is going to be like a sine wave that has the samples of a sine wave like this. And it needs to be the same exact length as the input signal. And our output is also going to be the same length. So the arrays have to be the same size. And instead, we're going to, this time we'll put a sine wave in here, or another kind of LFO, whatever we want to use, and multiply these things together to get some output over here. So let's take a look at how this can be done. I'm going to go back to have my original acoustic guitar over here. And now what I need to do is say this is N is going to be the length of X. So we're not defining our own length. We're keeping it based off of our input signal. Let's not overwrite the sample rate like this. Now what we're going to do is synthesize a sine wave based off of some frequency. Let's call this like 3 here. And now we're going to create a new output signal we'll call Y. And we'll also have some M, that is our modulator. In here, we'll create a sample for our modulator to use. It's going to be the sine of 2 times pi times f times t. So that is our LFO to use. And then down here, for y, this is going to be our x at the current sample number multiplied by our m at the current sample number. So very similar steps that we've done before, except we're calculating a sine wave to be able to use. Now there's a couple more operations that I need to do to take this sine wave and make it usable. We actually need to apply a gain and a DC offset to the sine wave for it to work. Let me draw this and explain why it needs to be this way. So by default, when we have a sine wave that gets synthesized, it's going to oscillate between +1 and -1. So these become the values that we're going to use to scale the amplitude of our acoustic guitar signal that's coming in. So when we multiply by 0, that means that it turns the signal into silence. That's okay. In this case, we can have it go up to an amplitude of 1, then come down here to amplitude of 0. But then what happens is we're going to be multiplying values to our signal that are less than 0, which we saw before is actually going to invert the polarity of our signal. The purpose, but that's not the purpose of tremolo. The purpose of tremolo is just pulsing. It's not ever intending to flip the polarity of your signal upside down over certain periods or stretches of your signal. So what we're going to do is we're going to take this, and we're going to modify it so that it only goes between 0 and 1. We go between 0 and 1, it's kind of like we're just fading the signal down and fading the signal in. Fade out, fade in, fade out, fade in. We're never going below 0. We can go all the way down to 0, and we can go up to 1. So this is accomplished by 2 steps. First thing we're going to do is here take our whole sine wave and multiply it by 0.5. What does that do? It takes our signal and now it fits it into a smaller range. It goes from 0.5 down to -0.5. So that's the result of an operation of multiplying by 0.5, but we're still going below 0. So now is where we put our DC offset in. DC offset shifts this whole thing up so that it occupies a range up here that goes from a signal like this. So now we're centered around 0.5. We go up to 1, and we go down here to 0. So this is our goal of the steps that we're going to apply to our sine wave. So I can come in here and do 0.5 multiplied by our sine wave plus 0.5 is our offset on it. So now what we can do is you can just go ahead and do a regular plot of t versus y on this. And here ends up being our acoustic guitar, where we introduce this pulsing effect. And if I play it back, it will sound way more interesting than me just trying to show you the visualization of it. But I played the wrong thing. Instead of plotting, that's the original, I need to do the output signal. So there's our tremolo. We can also change this to make it faster, so the pulses occur quicker. This is an audio effect that you would find on a lot of guitar amplifiers, where you'd have, it would be called rate, or like a guitar pedal would be called rate for it, that you could adjust. Or we could also make it slower. So yeah, that's a application of things that we've discussed in terms of changing the amplitude of something, synthesizing a sine wave, doing a DC offset, combining samples together to create new signals, and that kind of stuff. There's one more category of effects that I want to be able to demonstrate a number of things very quickly on, and that is of distortion effects, because I think distortion effects are very interesting, that cover nonlinear signal processing, doing things to our signal. So up to this point, a way to think about what we've accomplished is we take our signal X like this, and we apply to it some linear operation. So this could be addition, or it could be multiplication. And we use these operations in different ways, and that gives us some output signal Y. There's a whole different other category of effects that we can accomplish if we do other operations, so nonlinear stuff. And there's many, many different ones that I can cover in just a handful of minutes on this. So in terms of audio, we have these different kinds of distortion. That would be things like overdrive, or fuzz, or bit crushing, and saturation, or rectification. These are all variations of ways to distort our signal in different ways. And I can show you some of the common algorithms that we use that are meant to distort our signal in various different ways. So one of the ones that I can show you is for rectification on this. And this is where I'll draw a picture of this first one. Rectify the signal in different ways. So we have a sine wave like this. We can do something called full wave rectification. Which is to take that signal and turn the negative parts into positive. Something like that. So let me go back to, I guess we can take our acoustic guitar, and I'll just work off of this one. The easiest way to listen to stuff. In a way, this one can be accomplished is by using the absolute value, like this. So might not normally distort an acoustic guitar in this way, but for the sake of just having something quickly to listen to, we can do this. Let me go ahead and plot T and X on this one. You'll hear these while the plot is coming up of what it happens. Just try to keep in your head what the original acoustic guitar sounded like, and now it's going to be very distorted. So yeah, definitely distorting our signal there. We can see this thing happening where there's the parts of the blue signal that get reflected over and become positive. And there's also parts of the blue signal that are positive that stay positive with it. So that is full wave rectification. I can also show you another one that's called half wave rectification. This is where you take the positive parts and you preserve them, and you take the negative parts and you just set them to 0. So this is an opportunity to show some more control structures in MATLAB. This is going to be accomplished using something called a conditional statement, an if statement on this. So what we'll do is we'll say if the current amplitude of our signal here is greater than 0, then our output, y at the current time sample, is just equal to x at the current time sample. And if that condition is not fulfilled, so if our sample is less than 0, then our output is going to be equal to 0, like this. So a different way of distorting our signal sounds like this. So here you can see it tracks the positive parts, but then when it goes negative, it gets cut off, and it's just set to 0 for those. So that's a half-wave rectification. Both of these are types that you might find in a distortion plugin, like in your digital audio workstation, as common ones to see there. Another one that I'll quickly demonstrate is one that is associated with digital distortion. It's called hard clipping. Where if you have a signal, it is allowed to go up to some threshold, but then you just cut off the top of it. So you have this sine wave that gets cut off at these different points. And it, instead of the sine wave going up like this, it has these peak points that it allowed to exceed some threshold. So I'll quickly add that one in here. What we can do is set some threshold of equal to, how about 0.4 on this. And we'll say, if our signal is greater than our threshold, then our output is just equal to whatever that threshold is. We'll do else if x is less than that threshold, then our output is going to be, sorry, this should be negative threshold, equals negative threshold. And otherwise, we're going to just have our signal be equal to this one. So should be able to plot this one and see it. Do not want to do that one. Try this again. So probably these negative values are the ones where you can see it the most. Different way of distorting it, where like it goes above that value and then it gets cut off. It can drop below this value and then it gets cut off, but everything in the middle, it tracks just fine. So I normally think of that as like digital distortion, because we have these like a converter, and audio, an A to D converter, D to A converter has these fixed maximum and minimum values that it can pass the signal in between, but it will cut them off in the middle. One last one that I'll show, and then we'll have time for questions here, is one called soft clipping. So soft clipping is one that we normally think of in terms of analog distortion, but we can try and create it digitally using our own computations of it. So instead of having like these maximum fixed values that where things are getting cut off, what we want to do is take a sine wave like this, and we want to round it off in a smooth way. Round it off in a smooth way. So it's not, it doesn't sound harsh like this. So during some parts, it will track it pretty well, but then it will round off the top. And this is similar to what might happen with tubes, or like with analog tape, where it would just saturate as you push the signal up, not in a harsh way, but in a very gentle way, relatively speaking. So this is soft clipping. So I'll show you a common algorithm that's used for this. We don't need conditionals to accomplish it, so I can get rid of those. This is one that is called arctangent distortion, because it's based off a trigonometric function, the arctangent function. So we'll say that our output here at the current time sample is equal to 2 divided by pi. It's just the scalar that we put out front of arc. I think the MATLAB function is atan. Or atan of some, I guess we can just say x of this one. And usually we have like a drive parameter. So instead of threshold, we could say drive here. And this is a value that normally goes from 1 to 10. Think of it like a knob. If you're down at 1, then it's not a lot of distortion, but as you go up to 10, you can vary the amount of distortion on it. So I might start out with 5 here so you can hear it and then go through the different values. So what we're going to do in here is called drive multiplied by this one. So we scale the amplitude before it goes into the arctangent function to either increase the amplitude or drive it up more. And then this is just a scalar afterwards. So let's hear how this sounds. It shouldn't be as harsh as some of the other ones that cut the signal off completely. I can back this off to make it less. So very subtle distortion, and then we can go up to more extreme. So I think that's probably a good place to stop and open it up for questions. Tried to give you some practical examples of things related to processing signals in different ways, synthesizing signals, both linear operations and nonlinear effects. There's obviously plenty of more that we could cover. If you're interested at all, I have a website, hackaudio.com. I have a textbook that goes along with the website that you can learn more about other things like filtering and reverbs and echo effects and those kinds of things as well, compressors. So lots of different kinds of effects and programming and signal processing that you can get into if you're interested in these kinds of topics.